Friends, in our previous video, we have seen till the voltage divided by a circuit analysis, isn't it? So now today we will go for the Q point analysis, and also we will find out the endpoints of the load line. So here we will be seeing the voltage divider bias. So we have seen this many times, isn't it? So here we have the voltage source and we have voltage divider resistance R1 and R2, RC, then RE. So this is the voltage. So this is your base part, this is your collector, and this is your emitter, isn't it? So the base part is input part, collector part is your output part of the circuit. So at this base part, so the voltage which will be coming across your the voltage which will be dropped across your base to emitter will be what? The voltage across your R2, isn't it? The voltage across your R2 will be biasing the base circuit, and VCC will be biasing the output circuit or collector circuit. It will be biasing. Okay, so V2 will be biasing the base circuit. So V2 voltage here I can say the V2 as what? Voltage across R2, and VB will be the voltage drop across your base to emitter terminal. And next comes what? RE in the sense here there will be a voltage drop that we can say it as what? VE. VE will be the voltage drop across your RE, and the current which will be flowing here will be what? IE, and the current which will be flowing here will be that is what? IC. Fine. Okay. Is that okay? Yes. So what will be this current? This will be what? IB. Isn't it? So here we have the voltage divided by a circuit, and if I go for the circuit analysis, so we have discussed these things. Okay, so in the previous video we have derived these equations, and for V2 what voltage, what I can write for V2, what equation I can write for V2, what will be the V2 voltage? V2 voltage will be the flat voltage into the resistance divided by what? R1 plus R2, the sum of two of the resistances. Okay, so this is by the voltage divider rule. Okay, so this is by the voltage divider rule. So we have the voltage of across your R2 will be V2, that will be V2, and this is how I can give. And so we have discussed this, isn't it, in our previous video. Okay, so then after this I can write for IC. For IC I can write, if I go for this IC, how to get to the value of IC here. So here if I apply KVL at this loop, so we have discussed this, isn't it? So again I am telling the same things. So if I apply Kirchhoff's voltage law at this loop, so I can make out the value of IC, that is equal to what? V2 minus VB divided by RE. So how we can make out that? So I can go for what? V2 will be equal to VBE plus V2 will be equal to VBE plus VE. Fine. So V2 will be equal to VBE plus VE, and how I can write VE as IE into RE. VE I can write it as what? IE into RE, and as we know that IC will be equal to IE. Why? Because IB will be equal to what? IC will be equal to IE, approximately equal to IE. Why? Because IB will be very small. IB will be what? Very small. So IB will be very small. So I can make IE that is approximately equal to what? IC. I can write it as. Fine? Yes. So this is how, if I go for the substitution, so then I can rearrange the things and I can make out the value for your IC as what? V2 minus VB divided by RE. If V2, if you know that if a circuit has been given for you, if I have a voltage divider bias circuit, if I know the value of what? R2, R1 and VCC, I can make out the voltage drop across V2. Fine? Okay? Yes. After that, after finding out V2, I can directly find IC by knowing the value of V2. V2 minus VB. VB will be a set value for your transistors. For silicon, it will be so and so, and for germanium, it will be so and so. VB value will be fixed. Okay? Yes? Okay, so VB value will be given for a transistor. In the sense, silicon transistor will have different value for VB voltage. different value for your VBE voltage. Okay, so after all this, I can directly find out IC. IC will be equal to what? V2 minus VBE divided by RE. Okay, fine. So RE value obviously will be known by the circuit resistance, isn't it? So I can find IC, the collector current. So which will be the output current I can make out. If I apply the Kirchhoff's voltage, like voltage law, if I apply KVL at the collector circuit or the output circuit, we can say collector circuit is output circuit, base circuit is what? Input circuit, isn't it? If I apply the Kirchhoff's voltage law at the collector circuit, I can make out the final equation is what? VCE will be equal to what? VCC minus IC into RC plus RE. Because IC here, I can, what is the first equation what I can write? With the Kirchhoff's voltage law, if I apply here, so I can write that VCC will be equal to sum of voltage drops, isn't it? The applied voltage will be equal to what? Sum of the voltage drops. 3 voltage drops will be there. So VCC will be equal to IC RC, or what we can write it as what? VC. The voltage drop across your RC as VC plus VCE plus VE. Voltage drop across your RE. So that is what I will be writing. IC/RC for VC and IE/RE for VE, and as we know that IC will be equal to IE. If I substitute that value, so finally I will be getting this equation. Correct? Is that okay? So these two like the circuit analysis things we have seen in our previous video, isn't it? So now we will be coming for the Q point analysis. Q point analysis or not Q point analysis, we will come for the endpoints of the load line. So once you are done with the circuit and analysis, we have to go for the DC load line, and wherein we have to find out the endpoints of the load line. Here on the x-axis, we have cutoff point. Here we have the saturation point on the y-axis. So if I go for the same things, I have to consider. If I consider this equation again here, so VC will be equal to VCC minus IC into RC plus RE. So wherein if I have to go for this point, this cutoff point, if I have to go for, what will be IC? IC will be equal to 0 in the cutoff point, isn't it? In the x-axis, IC value will be equal to 0. That is what I am plotting. X-axis point, IC will be 0. I will be plotting, putting the value of IC as what? 0. Then this equation will reduce to what? VCE will be equal to VCC. Is that okay? So your VCC voltage, what you have applied is your cutoff point or VCE cutoff. Is that okay? Fine? Yes. So that will be your VCE cutoff. Fine? Yes. So if I go for the y-axis or y-axis point, if I have to go for that means what? Saturation point if I want to find out, then what I have to do in the saturation point, if I go in your if I go here at the y-axis, so y-axis will have VC will be equal to what? 0, isn't it? If I go for y-axis, the value of VC will be what? 0, isn't it? For this point, VC is 0, isn't it? So that is what I will be putting. VC will be equal to 0 if I put. So then your output, the equation will be VC value will be 0. If VC value is 0, so 0 will be equal to what? VCC plus VCC minus IC into RC plus RE, and then if I rearrange the things, I will come to a conclusion of IC will be equal to what? VCC. IC will be equal to what? VCC divided by RC plus RE. VCC divided by RC plus RE. I can go for, okay. So like this also I can find out if I know VCC, RC and RE, the values of all these things. If I know, so then I directly I can go for the Q point or endpoints of the load line. Endpoints of the load line I can find out with the equation. IC will be equal to VCC divided by RC plus RE. So this is one of the equation to find the endpoint on the y-axis, and this is the equation for to find the endpoint of the load line on the x-axis. This is for cutoff point. This is for saturation point. Is that okay? Yes. So now coming to Q point analysis. So after finding out the DC load line or endpoints of the load line, I can draw a straight line. So that is your DC load line. DC load line. Is that okay? Yes. So after doing this, so DC load line will be drawn, and after finding drawing the DC load line, I should go for the Q point analysis. I should analyze the Q point, and how to find out the Q point is, so for Q point analysis, we will again consider the equation was that the voltage drop across V2. Voltage drop across V2. So if I apply KVL at this base circuit, so what will be that V2 will be equal to what? VBE plus IE RE. IE RE is what? It is PE. Voltage drop across your RE. So IE RE. So when we know that IC will be equal to IE. So if like IC will be equal to approximately equal to IE, isn't it? So if I go for this substitution, so then I can make out this IC as, so here instead of IE, I will be writing it as what? IC. So then I can find out IC will be equal to what? V2 minus V3 divided by RE. So this is how I can go for what? The Q point analysis. Q point analysis in the sense, so for this Q point, what I have to do is, so I should find the value of VCE Q point. Okay, so for this direction, I should find what? I should find what? ICQ. Is that okay? I should find ICQ and I should find what? VCEQ. After finding these two things, those two things will go and meet at a point that is your Q point. Fine? Fine guys? Okay, so here what I have to do is, I should find, after finding out the DC, drawing the DC load line, I should go for Q point analysis. For Q point analysis, what I have to do is, so I should find VCEQ and ICQ and the intersection or the ICEQ and VCEQ values will intersect onto a point. So that point is called as what? The Q point. Okay, so that is what we are going to find. Here I am finding out the value of IC. So IC will be equal to what? V2 minus V3 divided by RE. So by this formula I can make out, and I will be calling this IC value which is here as what? IC is nothing but what? Your ICQ. IC is nothing but what? ICQ, that is equal to V2 minus V3 divided by RE. Is that okay? Fine. So this is the equation, very important it is. So this is the equation for finding out the Q point, like the IC value or Q point IC value, and on the y-axis. Okay. Yes. So I am now coming back to the same equation, or if I apply KVL at the collector circuit. If I apply KVL at the collector circuit, so what I can write that as VCC will be equal to what? VCE plus IC RC plus IE RE. Okay, when like if I substitute for IE will be equal to approximately equal to IC, so then because we know that IB will be very small, so I will substitute what? IC will be equal to IE, sorry, IE will be equal to IC, so then that will reduce to what? VCE will be equal to what? VCC minus IC into RC plus RE. IC. Okay, VC will be equal to what? VCC minus IC into RC plus RE it will be. So this VCE I will be calling it as what? VCEQ. Okay, VCEQ can be found by using what? This equation. So VCEQ will be equal to what? VCC minus ICQ. IC I will be taking it as what? ICQ what I have found here. Okay, so ICQ into RC plus RE. Fine. So this is how these two things will analyze what? ICQ and VCEQ together will define what? The Q point. So for defining the Q point, I should have to have ICEQ and VCEQ. So very important. These two formulas are very important. So this is how we can go for the Q point analysis. And here I can write the coordinates for the Q point as what? What are the coordinates? It is VCEQ, ICQ as the coordinates of this particular point. So that is called as Q point or quotient point. Okay, quotient point or quotient point, we can call it as the operating point. It is called as. Very important. It has to be like understood by each and everyone. Okay, so this is very important, and these analyses are very important, and these equations, these are all very important. So next we will see, we will solve a problem. By that we will understand how to go for the things. Okay. Yes. Now we have a problem which is on the voltage divider bias to find the end points of the load line and the Q point for the circuit given. So this will be the circuit given, and there sometimes they will be asking you to draw the DC load line too. Okay, so we have to draw the DC load line by plotting the graph of your DC versus IC. So and we have to draw the DC load line. It's not a measuring thing. So just for an idea, how much will be the portion of your VCB and what will be your IC. Okay, so now that also we'll see. And here we have a circuit for voltage divider bias. So using a silicon transistor. So they have used it as what? Silicon transistor, and silicon like type of transistor what we are using. Either it is silicon or germanium. FX value of what? VBE. Voltage conductor based emitter will be differing for silicon and germanium transistors. Yes. So now we have voltage divider circuit. So wherein we have a silicon transistor. So this is your collector, emitter and base circuit and collector circuit. R1, what is the value of R1? R1 is what? 10 kilo ohms. We have to correlate these things. Okay. So we have to remember all these things properly. Okay. Fine. Yes. So R1 value is what? 10 kilo ohms. R2 value is what? 1 kilo ohms. And this is what? This is RC. RC is 2 kilo ohms and RE is what? 1 kilo ohms. Fine. So we are done with the circuit and the voltage. What is that? VCC is what? 12 volts. Looking at this circuit, we have to make out all these things. After making out all these things, our first task is to find the endpoints of the load. This is a final question. Is that okay? So, and very important question, and it will be asked often. So many of the exams they have asked this question. Midterm and final exam, it will be one of the questions which will be there in your question paper. And to find the endpoints of the load line. So endpoints of the load line, to find that we'll go for the Q or point on the x-axis. So we have a load line. So I'll be drawing a load line. So I should find the point on the x-axis. This point I should find now, isn't it? So that is nothing but your VCE point I should find, or nothing but the cutoff point. So to point on the x-axis, to find that, what equation will we have? VC will be equal to what? VCC, isn't it? VC will be equal to what? VCC. So that is a unit 12 volts. 12 volts will be your VCE. So we have got one point, that cutoff point, or one of the point of your DC load line, the x-axis. To find out the point on the y-axis, what we have to go for is, so we have to go for a thing, or we have to consider the equation IC will be equal to what? VCC divided by RC plus RE. So when I know this RC value and RE value, so I can use this equation. IC will be equal to what? VCC divided by RC plus RE. So after putting the values, VCC is what? 12 volts. RC is what? 2 kilo plus 1 kilo. If I put those two values, it will come out to what? 4 milliamperes. 4 milliamperes is what? 4 milliamperes is what? Your the IC value, and this is what your endpoint of the load line on the y-axis. Is that okay? So if I consider this thing, so if it is 2 volts, this is 4 volts, 6 volts, then 8 volts, 10 volts, this is 12. Fine? Is that okay? Is that okay? Starting from 2 volts, 4 volts, likewise in that proportion. Okay. So this is 0. And here, if I go for a y-axis, if I take this as what? 2 milliamperes. If I take this as for 2 milliamperes, this will be what? What this will be? This will be what? 4 milliamperes, isn't it? This will be 4 milliamperes, isn't it? So this is IC, isn't it? In this direction. This is VCE in this direction. Fine. So this will be 4 milliamperes. So this is the point which is needed actually, isn't it? So this is your another point on the y-axis. So this is first point on the x-axis. So I will be joining those 2 points. This is nothing but your DC load line. So this is the thing to make out the endpoints of the load line and drawing the DC load line. Fine, clear, very easy. Okay, yes. So now coming to, okay, I will be drawing these things. Okay. Now coming to this side to find the Q point. Once we have found with the DC load line, then I should analyze, I should find the coordinates of the Q point as what? Q point's coordinates is what? VCE Q. Here is everything. Q point coordinates I should find. That is Q points coordinates is that VCE Q and IC Q I should find. So this is very important. So second part of this problem is this thing to find the coordinates. Okay. Yes. So now to find the coordinates, what we have to do is, so we know that first we should start with what? To find the value or V2 value we have to find, or voltage drop across here R2 we have to find first, because that gives the idea of what the voltage drop across here R2, and here will have the base circuit or base circuit bias voltage is nothing but your V2. Once you find out V2, you will get to know about what is ICQ. Okay, so for that V2 I have to find. For finding out V2, we have a formula. What is that? VCC into R2 divided by R1 plus R2 is the formula to find out the voltage drop across your resistor R2, that is V2 by voltage divided. We have this formula. So after putting the values 12 volts into 1 kilo ohm, what is 1 kilo ohm? R2 is 1 kilo ohm. So and then is that R1 plus R2. 10 plus 1 is what? 11. Okay, 11 kilo ohms. If I go for the solution, so we have to we'll be getting a value of 1.09 volts. Okay, fine. After that, so I should go for what? ICQ. For finding out ICQ, we have a formula. What is that? V2 minus VB2 by RE. So V2 value we have found that over there, isn't it? It is 1.09 volts. And what we have to go for is, now comes the question of VBE. What will be the voltage drop across base to emitter if it is silicon transistor? If it is silicon transistor, the value of VBE will be equal to what? 0.7 volts. For germanium it will be 0.3 volts. For germanium transistor, VBE value will be equal to 0.3 volts. Clear? So here they have given it as a silicon transistor. If it has not given in this circuit, here they will mention for the given circuit or given circuit having silicon transistor. Here they will mention the question itself. Okay, so either that or here they will mention this one silicon. So then I have to take this VBE value as what? 0.7 volts. Okay, so I am substituting those things. I will value is what? 1 kilo ohms. If I put all these values, that will come out to be what? 0.39 milliamperes it will be coming. After all this, so what I have to go for is, I should go for what? So I have found out ICEQ. ICEQ is what? 0.39 milliamperes. And after that, I should go for what? VCEQ. VCEQ, if I find out, so VCEQ will be how to find out VCEQ. For finding out VCEQ, we have a formula VCC minus ICQ into IC plus RE. Okay, so this is the formula. And if I put the values 12 minus 0.39, the value what I have found ICQ, isn't it? ICQ value is 0.39 milliamperes. I am putting that milli minus 3. Okay, so into 2 plus 1 kilo ohms. So that will come out to give what value? 10.8 volts it will be. So this is how I am defining also VCEQ, and finally I can define a Q point using the ordinal values of VCEQ and ICQ as Q is equal to 10.8 volts, 0.39 milliamperes. So if I go for that DC remote line, so wherein we had 12 volts and here this was 4 milliamperes, isn't it? 4 milliamperes was the point wherein we had endpoints. 4 milliamperes we have y-axis point and 12 volts we have x-axis point. So I should find the Q point where when the Q point comes, if this was 10 volt, in our previous diagram we have done this as 10 volts, 10.8 will, if this is 11, 10.8 will be coming somewhere here, isn't it? Somewhere here it will be coming. Okay, so somewhere here it will be coming. 10.8 will be coming somewhere here. Okay, so this is your VCEQ. Fine? Yes. So then ICQ is what? 0.39 milliamperes. 0.39 means for somewhere here. If it is 4, this will be 2, this will be 1. 0.39 means what? It will be coming somewhere here. Okay. So if I go somewhat like this, here will be a Q point. Here it is going to come. Fine. So this will be the Q point. What has been decided by this circuit. So this circuit component values will decide the endpoints and the Q point where that is going to come. So this is all about the Q point analysis and endpoints of load line, what you have to find out, and coordinates of the Q point, what you have to find by this formula. This is a 5 marks problem and a very important problem what we have to consider. Okay, so this is all about for today's class, and next class we will be seeing some of the important things about the leakage current and all, and that will be the last class for the second chapter. Okay, yes.